This video will review the Jupyter Notebook used to process EMT simulation results using Python. We showed this example in the August 3rd bootcamp session towards the end, but that work was not recorded. So just to help you follow along, you can start the notebook using a batch file or with Windows Explorer. I've shown in the repository there are 7 notebooks available. I'm going to start the one of interest just by typing the command notebook. It's a batch file that is going to start and open the Jupyter Notebook in my web browser, which is Chrome in this case. So there are in the gray cells different Python source code statements. The way this is set up, if you can see I highlighted that line, the data that we're going to use in this example is in a sibling directory called data, and then the root name of the Comtrade file is playback. So these are some old simulation results. The model isn't working properly, but it does lead to some interesting waveform behavior that makes for good illustration. To execute one of these commands from the cells, I'm going to import a lot of supporting libraries for plotting and numerical analysis, the Comtrade support library, and I'm going to load in all the channels from that playback file using these statements here. So I click the little play button here. I think I can show that in an arrow, this one right here. So if I click that play button, and scroll back up here, there were this little square bracket here used to be blank, and now it's got 1. So there's a like of a log functionality of the notebook that's each time I execute a cell, it's going to keep track of which one I did. The next cell is simply defining some per-unit bases and support routines to do some scaling of the waveform data. So I'm going to click the run button on that. And the little blue bar here shows that it was successful. And I'm going to click the run button a third time, and that is going to summarize the data that I just imported. So the way this is set up, I have 9 channels. I have 3 instantaneous voltages. This is VA, VB, and VC. And I've got the minimum and the maximum values. This is going to be kV line to neutral, I believe. The next 3 are the instantaneous currents, A, B, and C, and then A7, 8, and 9 are the RMS voltage, which is in per unit, and P and Q, which are in megawatts and megavars, respectively. And I've got a sign error in P, so it's negative. Well, actually, it's not a sign error, but it indicates that it's exporting power to the grid. The next plot, I'm going to skip over this because I don't want to use the Plotly interactive plotting library, but I'll go down, skip a couple, and I'm going to go to this cell, which I just highlighted, to run the plots using Matplotlib. This is going to happen pretty fast because I have a new machine, and I've got my channels plotted in a certain predefined format. So I've got the 3 phase voltages. You can't see those because it's 6 seconds worth of data, so you can't see those very well. But in the browser, this little toolbar shows up floating, and I've got a zoom to rectangle, so I can click on that, and I'm just going to zoom in on the currents, and I get a zoom in, and you can see what's happening, some instability in the currents there. This is a single line to ground fault, so in blue, VA goes down to about 50% voltage or so, and the 2 healthy phases, one of them rises. This is all pretty much as expected, and you can see the dynamic quantities, the RMS voltage. This is kind of a weighted average of the 3 phases, so the different ways you can calculate a single RMS value. So it's not that all the voltages drop to 80%, but one dropped to 50%, the other 2 really close to 100%. And you see some oscillatory dynamic behavior in P and Q, the orange and green traces. I have a possibility to zoom in on just a certain X range of interest and also a certain quantity of interest. So here I'm looking at reactive power Q. and I'm only taking the distance between the time from 0.8 to 2 seconds. And I know that a fault occurred because we set up the EMT simulations that way, but the fault actually occurred at 1 second. So I know in this case that that's the event time. You notice that I have a scroll bar in the cell, and so sometimes this is convenient, other times it's not. If I don't want that scroll bar there, I'm going to float my cursor over to the left of the scroll bar, and you see if it went to a little plus sign, I can toggle the output scrolling. And now the individual cell scroll bar went away, but I can just scroll the whole browser window and see, okay, this is what I'm going to look at. I want to do some numerical examples of calculating peak values, settling times, damping rates, and overshoot. So we notice that the Q value is not at 0 per unit to start with. It's got a negative value. Looks like about minus 0.15 thereabouts, and then some oscillatory behavior. There's a transient that's got a peak value, and it's going to settle at some value. Because I zoomed in here, it looks like the final value is 0.6 per unit, minus 0.6 per unit, but it hasn't really settled. It looks like there's still some settling to go on. Here, this next cell, there's more going on. I'm defining a signal for post-processing, and I'm windowing it on the area of interest. So I will not narrate each Python statement here, but if you want to use this code and understand it, I urge you to read it in more detail on your own with the NumPy documentation close at hand, which is available online. But I am looking at the range from 0.8 to 2 seconds, and I am identifying min and max, the average value, the initial value, the final value in that time range. So I'm going to click the run button there, and notice that I've got min and max Y values and the times that they occurred. So my final value, again, it's minus 0.604287 at about 2 seconds. For some of the quantities of interest, like rise times, we want to know the time between 10% and 90% of the peak value. So we're going to look at the starting value, and we're going to find the peak value, whether it's positive or negative, and we're going to measure times between 10% and 90% of that distance. So I'm going to click here to do the next evaluation, and now I have the starting time is 1.02 seconds. So I know with the EMT simulation that the fault was actually applied at 1 second, but it takes a little bit of time for the quantity of interest, Q in this case, to register a change. And I'm looking at a 10% change between that and the initial value and the final value. And by the way, the initial value is not 0, so I got to measure the distance between those. I'm going to now look at some figures of merit. So the reaction time, we have the slide deck available that defines all these terms from the August 3rd session. But I will run this code, and see, find this here. So as I said, the reaction time is 0.02515 seconds. And that's the difference between the 1.025, which when the event seemed to start from the Q data, and when I know it started, when I wanted it to start at 1 second. So there's a 25 millisecond delay, a little bit more than one cycle. I have a rise time of about 25 milliseconds. The settling time is 0.685 seconds. The overshoot is 0.95491, and I have a damping. There's two ways of calculating the damping. This first one is by overshoot, like how much overshoot there is from between the peak value and the final value. There's another way to calculate the damping, and that's by looking at log decrement. And so to do the log decrement, you've got to identify some relative peaks. And here I get a log decrement. That damping is 0.022. Whereas, based on the overshoot, it was 0.014. So it's not much damping. To look at this more visually, to really understand what's going on, A plot is going to be really helpful here, and that's this thing here. And I'm going to get rid of the scrolling in the cell. So this is my my original Q signal trace in green. The final value is 0.6 per unit, so I'm going to use the arrow highlighting here. So here's the final value, the last value plotted. I made some bands, the magenta lines here, and so the last time that the signal deviated from that magenta band is right there at that blue dot. And so the settling time then is the distance between the starting time of 1 second and this 1.685 seconds. So that's where I got up above the settling time here was 0.685. So that is how it was calculated, looking at these dots. And so the dots can be identified automatically just by scanning the wave form. So I, for example, to get the peak and the overshoot, I know the initial value here. This is where identify the peak there is minus 1.05 per unit. Going from this point here to this point here, that's 10% of the change. And so that's where I get my starting time, my event starting time. This is my peak value. This is my settle time. So the overshoot looks like it's almost 2 per unit based on that final value. To get the decrement by the damping factor by log decrement, I need these yellow dots here, which are the relative peaks. So I want to pick these out automatically. And to do that, I'm using another package called SciPy for Scientific Python, and I will scroll up here and show where that was done. Is this routine, that function that it has here called find peaks. And there are some adjustments, basically how wide do you expect the peaks to be relative to the event time. So there's a bit of a trial and error, some adjustment that to really make this robust, there could be some more work done on it. But if you look at the result here, you're getting a pretty good estimate of the decrement time in log decrement. I'm going to do one more thing, is the RMS sample waveform, the RMS error. This application is to show to get a single numerical representation of how much the event waveform is differing from the expected value. So I just put in a crude series of points that defines the yellow curve there, the orange curve, the base, and here's my signal, and I'm getting an RMS error of 0.0792 per unit. Okay, so if I'm going to zoom in here, notice that my yellow, my base, starts to change at 1 second, where the green doesn't really change. There's a little bit of a preliminary oscillatory behavior here, but doesn't really start to change in earnest until about 1.025 seconds. So remember that the RMS error there is 0.0792 per unit. If I'm going to change this, I'm going to show you what I'm doing. I'm going to change this 1.00 to, let's go 1.025. Okay, and now notice I have a little asterisk here next to my square brackets, indicates there was a change in the code, but I can re-execute it. And now if I notice my RMS error went down to 1.0519. So the RMS error went down almost 30%. If I zoom in again, you can see that the result is a little bit better, at least initially. So all these deviations, point-by-point deviations between the orange curve and the green one, there are lessened by this delay and the starting time. There are other ways you can look at that. You can calculate, what we already did. The event time, according to the green curve, is 1.025 seconds. We really wanted it to be 1.0 seconds. So anyway, this is an illustration of how the RMS error can give you a single numerical quantity to describe the difference between two waveforms. And the two waveforms could be different models, or between a model and a test specification, or a model and a field record. I'm going to go back and show some other differences. I am going to go back to several cells above, where this one here, so this is the seventh one I executed. I'm going to, rather than zoom in on 0.8 to 2 seconds, I'm going to use this value, the whole range of recorded data from 0 to 6 seconds. I'm also going to reverse the polarity. So in order to do that, I'm going to uncomment in Python the tstart and the tn, so it's going to override the first two values. And then I'm going to reverse the polarity by applying this -1 to the y data. So I'm going to, a lot of the signs have changed here, but the magnitudes are comparable. We'll execute the next one. So here my final value, before it was about 0.6 and now it's 0.9. I'm going to just click through all of these until I get down to where, and you'll see visually, and you can see more of this. So I'm going to click play one more time, and you'll see that the polarity of the green signal changed. So it is starting, at 0.16 per unit, and jumping up to looks like a 1.09, as before. The final value, though, is 0.9, and you can see that the settling time is longer. And it looks like the output has truly settled here. So in this case, if it was a real record, we want to make sure that we're using enough window of the data to get the proper result that we're looking for. The yellow dots are all identified properly as they were before. So we have more Jupyter notebooks on the repository and others in development to support IEEE 2800.2.